So our video today is an introduction to heat and specific heat capacity. And specific heat capacity, so if I have four objects here and I touch them, usually people will say metal feels colder than other objects. If you try this at home, if you have two objects that are sitting there, touch the metal, it feels cooler. If you touch something like wood or an eraser, it feels warmer. But if I check the temperature of all these things here, they are all, well, about the same temperature, 68 degrees approximately, okay? So different things, even though they have the same temperature, can feel different, and it's because they transfer heat at different rates. So I'm gonna introduce to you, so specific heat capacity looks something like this. Let's say I have water. Water is something we're familiar with, and it has a specific heat capacity of 4.18 joules per grams degrees Celsius. What does that mean? Well, when we have a term like this, we want to translate it into words that we can kind of make sense out of. So let's say I have 1 gram of water, and this cube here is about 1 gram. If it was actually a cube, 1 gram is about 1 cubic centimeter for water. And if I have this 1 gram of water, that means it takes this amount of energy up here, so 4.18 joules of energy, to heat up this 1 gram, so 1 gram of water, by how much? 1 degree Celsius. So I would need to take 4.18 joules of energy, I put in some energy here, and that's gonna heat up this 1 gram by 1 degree Celsius. Okay, so this is how the specific heat capacity looks. Sometimes it's written as a fraction like this, sometimes it's got a slash. What if I have some other objects? So we just looked at something like a metal, and metals, well, if I take a metal like copper, what do I know about copper? Well, copper, it heats up pretty quickly. If I touch copper, it feels pretty cool. So it heats up quickly, the metal heats up really quick. It also cools very quick. If I take a metal pan out of the oven, it cools down pretty fast compared to, you know, like pizza. So pizza has water in it and it cools down slowly. So copper, if you look at the specific heat capacity of copper, it's 0.385 joules per gram degree Celsius. What does that mean? Well, it takes a lot less energy for copper to heat up. So copper heats up quickly. So it heats quickly, but also cools quickly. Okay? If you take a metal pan of water and put it on the stove, the metal pan heats up really quick, but the water takes forever to heat up. We know that. So this is just how the specific heat capacity looks. If I had a cube of copper, it takes a lot less energy to heat up than it does water. What about something called molar heat capacity? So sometimes we use grams down here, and sometimes we use moles. And molar heat capacity is pretty much the same thing as specific heat capacity, except you're using moles down here. So for water, well, if I take this amount up here and I have 4.18 joules per gram degree Celsius, and what if I had 1 mole of water? Well, remember, in water there's 18.02 grams in 1 mole, okay? So if I took this number and multiply it by 18, my grams cancel out, but now I have moles in the bottom. What does that give me? Well, it gives me 75.3 joules to heat up 1 mole of water by 1 degree Celsius. So whenever I see this, remember, just try to translate it. 75.3 joules, it takes, right, 75.3 joules to heat 1 mole by 1 degree Celsius. Okay, now, what if the problem that gives you a Kelvin down here? So what if it says, well, 75.3 joules to heat up 1 mole by 1 degree Celsius. What about to heat up by 1 Kelvin? If you remember the Celsius scale and the Kelvin scale, they're scaled the same. They just start at different numbers. So if I go up by 1 degree Celsius, I'm also going up by 1 Kelvin. Because remember, Celsius and Kelvin is just Celsius minus 273. So if I go up by 1 degree Celsius, I'm also going to go up by 1 Kelvin, okay? And therefore, this should be the same. So it doesn't matter if I go up by 1 degree Celsius or 1 Kelvin, it's going to be exactly the same. So that's something to keep in mind. If I have Kelvin or Celsius, it really doesn't matter. So let's take a look at question 4 on page 6. And what if I have a piece of silver? So this is silver, 36.2 grams, and it's 85.7 joules to heat it up by 1 degree Celsius. Okay, so this is not specific heat capacity, because specific is per gram. It just gives me the heat capacity. It says, well, 362 grams of silver, and I want to heat it up totally by 1 degree Celsius. Well, what's the specific heat capacity? Well, I want to figure this out per gram now. So what can I do? I can set up a ratio, or I can just basically divide these things out. But I know that there's 85.7 joules for 1 degree Celsius. Well, what is it in 362 grams? Okay, so if I do this, divide it by grams, and that's going to give me this ratio now. It's essentially setting up a proportion. So 85.7 joules to heat up 362 grams. Well, how many joules is it to heat up 1 gram? If I do this and I cross multiply here and I divide by this, that's going to give me, I didn't solve for that. I'm going to do that right now. So 85.7 times 1 divided by 362. Well, I essentially divide by 362, and that gives me 0.236 or 7 joules to heat up 1 gram by 1 degree Celsius. Okay, so it's a low specific heat capacity, which matches what we know about metals. It's a lot less energy to heat up a metal than it is to heat up something like water. Okay, so what about figuring out how much heat it takes to heat something up? Heat is, because we now know how much energy it takes to heat up 1 gram of something, but what if I have different amounts of grams, and if I have different amounts of degrees Celsius? If I heat up something, if I heat up this rock, for instance, and I say I want to heat up this rock by 5 degrees Celsius, and this rock weighs 30 grams. Well, we can take this number and now figure out some stuff. And so heat, the symbol we use for heat is Q, lowercase q, and Q is going to be given as the mass of something times the specific heat capacity times a change in temperature. Okay, so delta T is change in temperature. Because if I heat it up by 1 degree, or if I heat it up by 5 degrees, it's going to make a difference how much energy it takes to heat that up. Okay, so here's an example. So let's say I have 15 grams of water, okay? And I heat it up, so instead of 1 cube of water, so I'm going to have 15 grams of water. So essentially, this is my 1 cube times 15 now. Okay, so I have 15 grams. And I'm gonna heat up from 25 degrees to 40 degrees. So instead of heating it up by 1 degree, I'm gonna heat up by 15 degrees, right? Okay. If my specific heat capacity is 4.18 joules to heat up 1 gram by 1 degree Celsius, how many joules of energy are required to heat up this water? Well, so I can set this up and use my equation. Intuitively, we can see that it takes 4.18 joules to heat up 1 gram by 1 degree Celsius. Well, now I have 15 grams. I'm heating up by 15 degrees Celsius. So we should take a lot more energy. So if I go ahead and set this up, Q is my mass, so 15 grams, times my specific heat capacity, 4.18 joules per gram degree Celsius. Make sure that these units line up. If I have moles here, then I gotta use moles here. But if I have grams here, I gotta have grams here. Okay, so this cancels out. Times my change in temperature, always my final temperature minus my initial temperature, because if I'm going up in energy, then that's a positive temperature change. So my final minus initial. This ends up being 15 degrees Celsius, as I was saying, positive 15. And my Celsius cancels out, okay? So then this times 15, what does that give me? 940 and a half, or 940. And my units are left over are joules. So that's my total energy it takes to heat up that much water by that many degrees. What if we have a negative temperature change? Let's say I have the temperature going down. It starts at 25, but it goes to 40. Sorry. Starts at 40 and drops to 25. So this is my final, and this is my initial. Well, if it drops, then you can see that this term is now negative 15 degrees. And so how much energy is it going to be? Well, it's just going to be a negative 941.5 joules, which means I lost energy. So joules says energy lost. So energy can be positive or negative. You got to make sure that you have a Q. This Q term can be going in is positive. So if it goes in, it's positive. If it comes out, it's negative. So energy lost or energy exiting. Okay, and so we can talk about what that means in terms of reactions later if energy is exiting. We looked at some energy diagrams last year. And then what if, let's say I have a different temperature change. Well, what if I go from 50 to 65? So my first temperature change was 25 to 40, right? So if I go from 50 to 65, is that going to make a difference? Well, this here is still plus 15 degrees Celsius. So if this is the same as 15 degrees Celsius, if these two temperature changes are exactly the same, well then it makes no difference at all because my equation only requires the temperature change, not the actual temperatures. So it's still going to be plus 940.5 joules. Okay, so temperature change. What if I go from 95 to 110? Well, it looks like it would be the same here, but we know that water, what happens at water at 100 degrees Celsius? It boils. So I would have a temperature change of 5 degrees Celsius for water here, but then something happens at 100 degrees Celsius, which is boiling, and that takes a different amount of energy, and we'll talk about that some other time. So I have to account for the energy of boiling. So boiling energy, this is gonna take a different amount of energy. So I'm gonna have to do this separate. And then I can go from 100 degrees to 110 degrees. And that's heating up. But this is heating up a gas. And a gas, how is that gonna affect my equation? Well, the specific heat capacity, this is for water as a liquid. And a gas is gonna have a different specific heat capacity. So that's something you have to think about if you're dealing with a phase change in the middle, but we're not gonna do that today. That will be for another time.